Hi, thank you so much for joining me. This is part two of a conversation about LeChatelier's principle. In the previous video, I spent quite a bit of time explaining how to use Q to justify or how to use rates to justify. So you might want to make sure you catch that previous video if you haven't already. So we have an equilibrium and we're going to have some stresses. In this case, volume is increased. So if I increase volume and my moles are constant because I haven't added any gas, my temperature is constant because I didn't change the temperature, that means I have to decrease the pressure. Okay, partial pressures are decreased. And what that does is we're always going to then counteract that decrease, to relieve that stress, is we need to shift in a direction that will increase the pressure to counteract that decrease in pressure. And to do that, you go to the side with the most, it shifts to the side with the most moles of gas. In our case, this is a gas phase reaction. You should recognize all of these as gases. And we have 2 moles of gases on the reactant side, nitrogen and oxygen, and we have 2 moles of gas on the product side. So in this case, because they have the same moles of gas on both sides, increasing the volume will have no impact. There's really no stress to that equilibrium. It has not shifted away from equilibrium. Now, the second one is temperature. If we increase temperature, an increase in temperature always favors the endothermic direction. It increases all rates forward and it increases the rate reverse. So both rates are increased, but the thermodynamic favoring of endothermic is what is going to cause the shift. And we're going to reestablish equilibrium. We want to favor the endothermic direction. In this example, it's endothermic in the forward direction. So what will happen here is we are going to increase our partial pressure of product, or we're going to increase the molarity of product. And the only way we can do that is to consume reactant. So we're going to decrease our reactant, either molarity or partial pressures. So that's how you would evaluate that. An increase in temperature favors the endothermic direction, and if it was a decrease in temperature, that always favors your exothermic direction. By removing the heat that is formed, you facilitate that exothermic direction. All right, here's some more examples with some solubility questions. And when you are adding substances, you want to ask yourself 2 questions. Is this substance you are adding part of the equilibrium? And if it's not, 2, you want to ask yourself, will it react with a species in the equilibrium? Sometimes that's how we decrease a substance, is if I can cause it to react and precipitate, then I can remove it from my equilibrium system. So you always want to ask yourself that as you're adding these things. So this is about slightly soluble salts. So if I have AgCl solid and it is a saturated solution, I have aqueous silver chloride. So I've got aqueous ions. Anything that dissolves will dissociate. And the stress in this case is adding calcium chloride. Well, calcium chloride is a soluble salt. It will go 100% to calcium ion, aqueous, plus the chloride ions. Calcium ion is not part of the equilibrium, nor does it react with anything in the equilibrium, but the chloride is part. So what we're going to be doing is we increase the chloride concentration. I have more collisions, so my rate reverse increases. I've increased a product, so Q becomes greater than K. And both of these mean that we're going to shift to the reactant side. And so what that means is we're actually going to decrease the solubility. So we will have a decrease in the solubility. I'll make more solid. If there was no solid present, I would precipitate that. I would get a more silver chloride precipitate in this case. Another way of thinking of it, if you add, you subtract. And the way to subtract is to consume product and form reactant in this case. All right, the next one looks like it's similar, but there is a caveat here. So here we go. We've got our lead chloride equilibrium. It's a slightly soluble salt. I'm going to get lead ion and 2 chloride ions. And the question says we add more lead solid. We've increased our lead solid. Well, this is a saturated solution. The solid is not part of K. Remember, KSP would be only the lead ion. I didn't add. Had I added lead nitrate, I would have increased my lead ion, but I didn't do that. Had I added sodium chloride, I would have increased my chloride ion. I didn't do that. I just popped in some more lead chloride. The addition of solid does not stress or shift. So if you add a solid, there's no stress, no shift, no effect. Okay, let's take a look at this next one. We have slightly soluble calcium hydroxide. So I'm going to do this. So calcium hydroxide, all right, and it's considered a strong base, so it does go pretty far to the right, but not completely. It does set up an equilibrium situation. It is here, okay, and these are both aqueous, and that would be in equilibrium with the solid. Now, if I added a strong acid, I'm adding H+. That's what a strong acid provides for us. There's no H+ in the equilibrium reaction. So that's questions and no, that's not the effect. But remember I said the next question you need to ask yourself is, does the added substance react with something? And in this case, the answer is yes, because H+ reacts with OH- to form H2O. So what we've done is we have decreased our hydroxide concentration. What's that going to mean is that I've shifted away from K and I now have Q. And if I've decreased product, that means Q is less than K because I've decreased product, and product is in the numerator. And when K is greater than Q, we always shift to the product side. So remember, if you remove, you must replace. So our mass of solid would go down and we'd get more calcium ion. And as we went back to equilibrium, you would increase your hydroxide concentration. All right, if instead we added a strong base, we're adding hydroxide ion. Hydroxide is part of the equilibrium. So if I increase my hydroxide concentration, I now have a QSP that is greater than my KSP. So if you add, we need to subtract. The only way to subtract a product is to shift to form more reactant. Okay, so in this case, I would increase the mass of solid that has formed. I'd precipitate more solid. I would decrease my molarity of calcium ion. And now to relieve the stress, now I know initially I have an increase in hydroxide, but to relieve the stress, it will go down from that point. So what happens is, in terms of your hydroxide concentration, it will spike up with the stress, and then as the stress is being relieved, the equilibrium is shifting, it will come back down. And this is the typical answer to that. So, okay, thanks for joining me, and good luck with chemistry and Le Chatelier.